When it comes to the world of computers, there's one thing that rules them all: speed. We want our search results now, we want our games to run without a hitch, and we want our data sorted instantly. This is the story of that relentless quest for speed. It's a journey right into the heart of how computers actually think. So let's dive in.
And this quote right here, it just hits the nail on the head. It tells us the fundamental truth that's driving almost everything in modern tech. It's not really about crunching numbers anymore, it's about managing information. Finding that one specific email or that photo you took years ago from this massive ocean of data and doing it in the blink of an eye.
I mean, that's the real challenge, right? When you're talking about the scale of data we have today, billions of websites, trillions of files, how in the world do you even begin to find what you're looking for? It feels like searching for a needle in a haystack the size of a galaxy. But as we're about to see, it's not impossible. Not at all. All right, so to even start tackling this, we've got to wrap our heads around the sheer scale of the problem. We are living in the middle of this unbelievable explosion of information, and every single bit of it needs to be stored, managed, and, you guessed it, retrieved.
Just picture it. This is exactly what our digital world would be without any kind of system, just a giant, chaotic mess. You could literally spend your entire life digging through that pile and still never find the one book you were looking for. That's the problem of raw, unorganized data.
And this is where we need a system. Enter data structures. These are kind of the heroes of our story. Think of them as the perfectly designed, super smart shelving systems for our massive digital library. They're the clever methods we've come up with to bring order to all that chaos, which is what makes our data searchable and actually useful.
Okay, so we get it. We need to be organized. Now, let's take a look at a couple of the most fundamental shelving systems that computer scientists use to build, well, pretty much everything in our digital world. So this slide shows something really important. There's no single best way to organize everything. On one hand, you have an array. Think of it like one long fixed bookshelf. It's amazing if you want to jump straight to the 100th book, but it's a total nightmare if you need to squeeze a new book into the middle. On the other hand, you have a linked list. This is more like a scavenger hunt where each book has a clue that points you to the next one. It's super flexible for adding and removing books, but finding that 100th book, well, you've got to follow 99 clues to get there. And this brings us to one of the most fundamental ideas in all of computer science, the space/time trade-off. The bottom line is you can't have it all. Do you want things to be lightning fast? Okay, but you might need to use up more memory. Want to be really efficient with your storage space? Well, you're probably going to pay for it with slower performance. It's always, always a balancing act.
And believe me, these shelving systems can get way more sophisticated. If you need to find a city by its exact name, you can use something called a hash table, which is so fast it feels like magic. But if you need to find all the cities with a population between, say, 1 and 2 million, then a totally different structure called a B+ tree is the perfect tool for that job. The key takeaway here is pretty simple. Different problems need different structures.
So, our library is organized, the data is all on the shelves, looking neat. Now what? Well, now we need a really efficient recipe to actually do something with it, like sorting all those books by the year they were published.
And that recipe has a name. It's called an algorithm. It's just a set of step-by-step instructions. Think of it as the recipe our digital librarian follows. A good recipe gets the job done fast. A bad one? It could take centuries. Choosing the right algorithm is every bit as critical as choosing the right data structure.
So here's a super simple recipe for sorting. It's called selection sort. You just, look through the whole list for the smallest thing. You stick it in the first spot. Then you look through the rest of the list for the next smallest, put that in the second spot, and you just keep doing that. It makes sense, it's straightforward, but yeah, it's a total brute force approach. And that brute force approach, it comes with a huge cost. Its performance is what computer scientists call n-squared. Now, in plain English, that means if you double the number of things you're sorting, the time it takes doesn't just double, it quadruples. For any kind of large data set, this isn't just slow, it's completely, totally unworkable. But what if we try a much cleverer recipe? Heap sort is a great example. First, it spends a little time up front organizing all the data into this really special, super efficient structure called a heap. And once it's in that structure, it can just pull out the largest item, then the next largest, and so on with incredible speed. It's a bit more complicated to set up, but wow, the payoff in speed is just enormous.
So we have our simple recipe and our clever one. But how can we really, truly prove that one is better than the other, no matter what kind of computer it's running on? We need some kind of universal ruler to measure how efficient these algorithms are.
And this is where computer scientists use this really powerful tool called asymptotic analysis. Don't worry about the fancy name. The main idea is actually pretty simple. Instead of measuring time in seconds or minutes, we measure how the amount of work grows as the size of the input, which we call n, gets bigger and bigger. We're focused on the rate of growth.
And this chart, wow, it tells the whole story. The n-squared algorithm, like our simple selection sort, just skyrockets as the input size n gets large. But an n-log n algorithm, like heap sort, grows much, much more slowly. And for a huge dataset, we're not talking about a difference of seconds or minutes. This is the difference between possible and impossible. So, for decades, the hunt was on for even faster sorting algorithms. I mean, n-log n is great, but could they do better? Could they find the absolute fastest possible recipe? The answer they found was just astonishing. This is it. This is the climax of our quest. Scientists actually proved that for this kind of sorting problem, there is a cosmic speed limit. It is mathematically impossible to invent a sorting algorithm that compares items and is faster than n log n. That means clever algorithms like heap sort aren't just fast, they're asymptotically optimal. They've basically reached the theoretical speed limit for this kind of problem. You know, hitting a fundamental limit like this is a really profound moment in science. It doesn't just tell us what we can do with computers, it also tells us what we can't do. And it points us toward the next generation of great challenges. So why does all this theory matter to you? Because these principles are running your life right now. The reason you can search Google, the reason your social media feed refreshes instantly, the reason your phone finds a map route in seconds, it's all because brilliant engineers chose the right data structures and the most optimal algorithms to make it happen. Every single one is a victory in this quest for speed. But the quest isn't over, not by a long shot. There's this whole other class of problems out there called NP-complete that are just terrifyingly hard. A famous one is the traveling salesman problem. Find the absolute shortest route to visit a list of cities. Now, we can easily check if a route is correct, but to find the best one, no one knows an algorithm that's much better than just trying every single possibility, which becomes impossible ridiculously fast as you add more cities. And that leaves us with this final, really fascinating question. For these fundamentally hard problems, is the solution just a more clever recipe that we haven't discovered yet? Or have we hit a limit that's going to require a whole new kind of computer, something like quantum computers, to ever break through? The quest for speed, it continues.